Hello there. Welcome back to your favorite place, the Math Fun Room. Good morning, good afternoon, good evening. I don't know what time it is, but it's math time. So in today's video, what we're going to do is discuss average value. So remember, in this chapter, we've been discussing applications of integration. So in this video, we're going to take a look at another application, which is finding the average value of a function. Now, obviously, you probably are pretty familiar with averaging numbers. I mean, if we think about, finding the average of 81 and 82 and 83 and 84, right? We would find an average. Usually in a statistics course, we denote this x bar, and we would add all the numbers together. So we'd 81 plus 82 plus 83 plus 84. And then we would divide by 4. So if we calculate this number, we're going to get 82.5 as our average. So a couple things to point out to ourselves here. First of all, what we're doing for an average is we're summing all of the data points. So we're summing up each x sub I as I goes from 1. And we went to 4 in this case, and we divided by 4. Now, in this scenario, right, the average that we ended up with, 82.5, isn't an actual data point, right? We don't have 82.5 in our data set of 4 numbers. Okay. So some basics of arithmetic there, to just a quick refresher of what an average is, how we would average a finite set of numbers. Now let's suppose we had, n numbers. So in this case, n was 4, right? So if we're finding the average of n numbers, right, technically, right, we would find the sum of all the data points, x sub I, as I goes from 1 to n, and we would divide by the n numbers. That would be the average of n discrete data points, or a finite data set. And what we're going to take a look at in this section, right, is suppose we have a continuous function. How would we find the average of the function? So to just draw a real quick rough sketch here, let's say I have some function that looks like this, and we're looking on an interval from a to b. Let me extend my axis here. And we're looking for an interval from a to b. So we have a smooth continuous curve, and we want to find the average function value. Now, the difficulty is here that we have infinitely many function values, right? If we think about all the y values on this graph, we're trying to find the average of every y value, right? How many y values are on this segment of the graph? Infinitely many. So a typical tool, right, that we use in a calculus course, and we've been using in this chapter, is we want to estimate. We're first going to estimate the average value of a continuous function, and then we're going to use the limit process to develop the average of the infinitely many values. Right, so we could start with choosing a finite number of values on the function. So for example, let's say I pick the first data point, f at a, right? Here's f at a, if you will, and then I pick this data point at that x value, and then I come to this x value and find that data point, and this x value and find that data point, and I would continue in this process, right? Now, what we would typically do, right, we pick a number of n data points, if you will, right? N could be 4, like we just saw in that example. N could be 10, n could be 20, n could be 50, and that's always our process, right? Our process says we're going to estimate with a finite number of n data points here, and then we're going to let n go to infinity, and we're going to get the true average value instead of an estimate. So if we think of a formula, right, let's say we have the average value, right? Most textbooks do like f sub average, right? And that's going to be approximately the sum of the data points. We are averaging the function values. So I have the function value at each x, and we're going to have n of those values. I go from 1 to n, and we're going to divide by the n data points that we collected. Now, just like we did with area under a curve and volume, we want to make things as simple as possible on ourselves in the sense that each of these widths, these delta x's, we want to be equivalent, right? We want them to be the same size, if you will. So if I'm cutting this graph, between the interval of a to b, I'm cutting the graph into, 10 data points. I want the distance between the data points to be equal, to be consistent. Now, we don't have to do that. Right? We technically could pick different delta x's, but just for simplicity, we don't. And because in the limit process, ultimately, that width doesn't really matter. We're letting n go to infinity in that case. All right, now what we will do algebraically is we're going to make the connection between delta x and n. So as we've done before, right, we find our delta x by finding the length of the interval b minus a and divide by how many segments we want. So if I solve this for n, I'm going to multiply the n to the other side and then divide by the delta x. So my n is b minus a over delta x. So I'm going to plug that in for my n value here. And we're going to have that the average value of the function is approximately going to have the sum of all of the y values that we're using, the discrete number of y values, right, the n of them, and then my n is b minus a over delta x. And I'm going to go ahead and flip and multiply this, right? So if I flip and multiply this, I get f of x sub I, have my sigma, right? And then I have, let's see, delta x over b minus a. So we have those in data values. And again, this is the average approximated with the n data values. And the beauty of the tool of the limit process, right, is it's going to allow me to find an exact measurement. So I want all y values in the interval from a to b. There's infinitely many. So we're going to say the average of the function is exactly equal to the limit as n goes to infinity of this expression. Right? So I'm going to go ahead. Technically here, I have 1 over b minus a. So I'm going to pull the 1 over b minus a out of the summation symbol because it doesn't involve any of the particular values in relation to this limit process, right? N is going to infinity, right? So the n is our limiting value. And so this is just a constant number, right? Again, if I'm going from 5 to 10, this is 1 over 10 minus 5. So it's a constant, so I'm pulling it out of that limit process. And again, as we saw in prior chapters, right, as we defined actually, right, what we have is a limit of a Riemann sum. So we have a Riemann sum here, and the limit as n goes to infinity, right, is the same thing as delta x going to 0, right? So as we squeeze more and more divisions into my interval, the delta x is getting smaller and smaller. And so this Riemann sum becomes an integral. So we have the constant 1 over b minus a, and then we have the integral of all the function values, right? So there's our formal definition. If we're finding the average value of a smooth continuous curve over an interval a to b, we're going to have this integral calculation that we're going to compute. So let's take a look at an example of this concept here. Let's do a calculation. So let's say we want to find the average value of the function f of x equals 1 plus x squared on the interval, let's say, minus 1 to 2. So the formula we just developed, right, says that the average value of this function will be 1 over, let me go ahead and just rewrite the formula, 1 over b minus a, the integral from a to b of all the function values. Right? So we're summing up all the function values. So in this case, our a is -1 and our b is 2. So I'm going to have 1 over 2 minus -1, and then the integral of my function is 1 plus x squared dx, and again our interval is from -1 to 2. So I'm going to crunch this integral. It's going to give me the average value. And then what I want to do is stop and discuss a couple conceptual ideas here. All right. So let's see, first of all, I get 1 over 2 plus 1, which is 1 over 3, so I have 1/3. I have the integral of 1 plus x squared. And then now we're going to find the antiderivative here. So the integral of 1 is x, so let me keep my constant here. So the integral of 1 is x, and integral of x squared is 1/3 x cubed, and we're going to evaluate from minus 1 to 2. So again, the fundamental theorem of calculus says I'm going to take this antiderivative, I'm going to plug in the upper limit of 2, and then I'm going to subtract with the lower limit of -1. So let's plug in let's plug in positive 2. We're going to have 2 plus 1/3 2 cubed, and then minus, and then we're going to plug in the -1. And we're going to work this out. All right, so if I come over here, this first term, and I distribute, so I'm going to have 2/3, and then this is 8/3 times 1/3, so this is 8/9. So I think I'm going to run out of room over there. So I have 2/3, and then plus 8/9, and then, you know, -1 distributes with -1/3, so I get positive 1/3, and then this is, you know, -1 cubed is -1, so this is -1/3 times -1/3 is positive 1/9, and I'm going to get a common denominator here of 9. So let's see, I got to multiply this first fraction by 3 in the denominator, so 3 in the numerator. And then the second fraction already has the common denominator of 9, multiplied by 3, and then already have the common denominator there as well. Right, so what do I have here? 8 plus 3 is 11, 12 plus 6, so I get 18/9 as my average value. And that is the number 2. So I want to scroll back. Actually, you know what? I didn't even graph this function, did I? So let's go ahead then and do a real rough sketch of this graph, and then I'm going to pull out Desmos and graph it as well. So for graphing this parabola, so we're looking at it was 1 plus x squared, right? So x squared plus 1. There's my parabola shifted up 1 unit here. And we're going from -1 to 2. So we're finding the average value of this function, right? So again, we've started here and we've added all the y values to find their average. Now, there's a really unique way to visualize this, and that is the following. We have found the average to be 2. So what we could do, let me use a different color here. What we could do is if we think of where is y equals 2. Let's see, here's y equals 1. Let's see, what's this y value at x equals 2? Let's see, it's 2 squared, which is 4 plus 1, which is 5. So technically this is 5. I didn't scale this very well. So let's say here's y equals 2. Right? So if I graph y equals 2, I'm looking at something like this. I'm looking the rectangle that I have here, right? So this is taking the average value in a visual manner. So in other words, if we think for a second, the integral that we found, what we've done in the past is we interpreted this integral as the area under the curve. So this integral of 1 plus x squared from -1 to 2 is technically the area under this curve. So if I graph this curve here and I sketch its area, that is what this integral is calculating as 2. Is that area. What we can interpret this rectangle as being is that same area. So think of a volume, and I don't want to say volume, right? Well, think of a cross section of some figure that we have here, and we have found the area under that figure. If this was a liquid and we let the liquid settle, it settles into this rectangle that we have here. So we could visually interpret the area under this curve from -1 to 2 as also being the same as the area under the curve. Remember, this was the curve y equals 2. And the reason that we mention that is what we're going to do in just a moment is we're going to look at the mean value theorem of integrals. And this is going to be a nice visual interpretation what the mean value theorem of integrals is telling us. Now I want to come back for a second because I just noticed that I have an error here. This integral is not 2. Right? It was 1/3 times that integral. That was 2. All right, so I want to take a look at one more quick example, and then we're going to move on to the next thing I want to talk about here. So let's say that we want to find the average value. Find the average value of the function f of x equals root x. And let's look on the interval from, let's say, 0 to 4. Now actually what I want to do here is I want you to pause the video and I want you to try this one on your own. I want you to use that integral definition, right? So the average value of the function is we're going to integrate f of x from a to b, and we're going to do 1 over b minus a. So pause the video, try this, find the average value, and then when you're done, unpause, and we'll take a look at this together. Alright, while you had the video paused, I sketched a picture of the graph real quick. So here's the picture of our root function, rough sketch. Our root function, we're finding the average value over the interval 0 to 4. So again, we're looking at these infinitely many y values over this interval, and we are finding the average of all of those y values. So we're going to use our average value integral that we developed. So for this example, we have 1 over b minus a, the integral from a to b of f of x dx. And then just to remind you, I'm going to go ahead and use the magic of erasable ink pen. Is the root function we're always going to write as a rational exponent so that we can use the power rule here. So the integral of x to the 1/2, I'm going to add 1 to the power, and then I'm going to multiply by its reciprocal, and then I'm going to evaluate from 0 to 4. So in this case, I'm going to go ahead and pull this constant of 2/3 out. So let's see, the 2 and the 4 simplify, and I get 1 over 6. And then I have, let's see, I'm going to plug the 4 in. So I really have, what do I have? The square root of 4 cubed, and then minus the square root of 0 cubed. Obviously this is 0. So the square root of 4 is 2. 2 cubed is 8. So I have 8/6, which is really 4/3. So that's the average value the average value of the root function. All right, I want to discuss a couple conceptual ideas here. And the first being that in order for this integral to really work, we have to have a function that's continuous. Let's take a look at an application where we have a graph and not an equation. So I stole this problem out of Stewart's book. And what we see here is a graph that's provided. And what this graph is giving me is the velocity of a car traveling for 12 seconds. So the car starts from rest, right? We have 0 velocity, 0 kilometers per hour, and then the velocity increases. So we have some data that we've plotted, and we have the graph of the velocity function. Now, a problem of this nature would probably say something along the lines of find the average velocity. Find the average velocity for the first 12 seconds, right? So let's say 0 less than or equal to t less than or equal to 12. So if we're using our average velocity formula, right, we're looking at the integral of 1 over b minus a times the integral from a to b of the, f of x dx. Now in this case, we technically have f of t dt, right? Our domain is t. So for the first 12 seconds, I'm going to have 1 over 12 minus 0. I'm going to stop for a moment because we can't actually evaluate this integral because we don't have an equation for the function. So as we mentioned a minute ago, we can interpret this integral as area under the curve. So when we're integrating f, we're finding the area under the curve. And what I'm going to do is use, some approximating rectangles. So I'm going to choose a delta x, let's say, of 2. So I'm going to have this delta x of 2, this delta x of 2, this delta x of 2, so on and so forth. And I'm going to use right-hand rectangles. Right? So this first rectangle, I'm going to come up, find that area. The second rectangle, I'm going to come up, find that area. Third rectangle, come up, find that area. Right? So my delta x is 2. So I have 2. Actually, I'm going to use another parenthesis right here, right? So if I'm using the right endpoint, I'm finding each of those function values to find the heights of the rectangles, right? So for this first rectangle, it looks like 20 is that right endpoint. And for the next rectangle, I'm just shy of 40. I don't know, let's call that 38. And then for the third rectangle, it looks like we're right at 50. And then for the next rectangle, it looks like we're right at 60. Let's go with 60. And then we looks like we're a little shy of 70. I don't know, let's call that 66. And then the last one, we are at 70 kilometers per hour. All right, so I paused the video for a second so you didn't have to watch me do arithmetic. So if I multiply all of this out, I get 50 and 2/3, right, or 50.666666 repeating. So my average velocity is 50.66666 repeating kilometers per hour over those 12 seconds. All right, so that was our estimate using right rectangles with a delta x of 2. And just to point out to you here, you could use a couple different approaches, right? What we could have done is, let's say, used midpoints. So let me grab my eraser. And erase all of my sketching on here. What we could have done, again, is used, let's say, midpoint. So we could have done a delta x of 4 and then use the midpoint of that interval to find, the area of that interval of a delta x of 4. Then we could do the next delta x of 4, and we would use the midpoint here to find the height of that rectangle, and then another delta x of 4, and here's the midpoint here to find the area of that rectangle. So if I was doing midpoints, right, I would have a delta x of 4, so I would have something like this. Let me switch to green just to sketch out what we're discussing, right? So I would have an average of 1/12, and then I would have a delta x of 4, and then my 3 midpoints were 20, 50, and I said 66. So if I took a midpoint approach, this would be another way to estimate that integral. All right, now crunching that out on my calculator, I get 45 1/3 kilometers per hour as the average velocity. And again, keep in mind, because we're estimating, each of these are estimates, right? So we're getting slightly different numerical calculations from our estimates. So one last thing I want to mention is when we compare these two answers, right, we notice that with the right rectangles we get a slightly larger number, right, and with the midpoints we get a slightly smaller number. And keep in mind that if we were to do left endpoints, I'm going to come back and use my eraser here. If we were to use left endpoints based on the shape of this graph, right, we would end up with an underestimate as well, right? So if I came back to a delta x of 2, my left endpoint here has no height to that rectangle, and then my second rectangle, I use my left endpoint here, and then my third rectangle, I use my left endpoint here. Right? So because this graph is increasing and concave down, right, my right endpoints have extra, my left endpoints are an underestimate. So remember that in a prior video when we discussed estimating integrals, the midpoint really is the most accurate. So that's why when we choose a delta x of 4, right, we see that midpoint has a little bit of extra area right here, a little bit of under area right here. So we really get kind of the best of both worlds with our midpoint. We kind of average out to some extent the excess and the underestimate. Again, from 4 to 8, I have that midpoint here that's going to come up. All right, I'm going to create that rectangle. I have a little bit of area here that I'm missing. I have a little bit of area here that's extra. So if we're not given instruction to use the midpoint, we do have options. We could use the left or right, but really the best choice is to use the midpoint, even if we're not given instruction.
So the last thing I want to discuss with you guys here is the mean value theorem for integrals. Now remember, back at the very beginning of the video, we reminded ourselves of the basic idea of an average, and I believe what I picked was like 81 plus 82 plus 83 plus 84. We were finding the average of those four numbers. And we pointed out that that average would be 82.5. So in general, if I'm averaging a discrete set, a finite set of numbers, the value that I get out of the average does not have to be an actual data point within the data set, right? We can see 82.5 is not in this data set. However, when I'm looking at a smooth continuous curve, so if I just do another rough sketch here, one of the things we talked about, and we looked at visually a couple minutes ago, was that if I find the average value of this function that is equivalent to, let's say, something like this, right? Looking at the height. So let's say here was my average value of my function. If I graph y equals that number, it's like letting the curve kind of settle and become flat, like if it was a fluid in a glass, or we said about 5-10 minutes ago. So what we're going to do with the mean value theorem of integrals does is takes a look at this concept. And in other words, there's a y value on this graph. Let's say it's at x equals some number c. So between a and b, there exists at least one number in the domain, let's call it x equals c, where the average value of the function, there is actually a y value that possesses that value of the average. Again, in our first example, this value that is the average, it is not a data point in this set. But because we're dealing with a smooth continuous curve, there's going to be at least one point in the domain where that y value is equal to the average value of the function. All right, and this is called the mean value theorem for integrals. So with something like this, right, I'll scribble this out. I'm not going to get extremely rigorous, but there's some number c in the domain of a to b where that is the average value of the function, right? We have 1 over b minus a, then integral from a to b, let's say f of x dx, right, where c is somewhere in the interval from a to b. I got a little righto there, a little typo. So there's at least one c value. There could be multiple. Right? And the way I sketched this, it looks like there actually is a second one here, right? Something along those lines. So just to take a look at a quick example of this, and as a time saver, I'm going to come back and use, excuse me, the very first example that we looked at. So the very first example that we looked at was we found the average value of f of x equals 1 plus x squared. The interval was minus 1 to 2. So when we found that average value, that's weird, things disappear sometimes on this digital board. So we found that average value to be, well, I think it was 2. If I scroll back up and take a look, I'm pretty sure that that was 2. Now if we look visually at that graph, and I didn't do a very good job sketching that graph earlier, but something roughly like this, right? Like, so here's 1 plus x squared, something like that. And at negative 1, we have there, and then at 2, so what were those y values again? At 2, I'm going to have 5. This was 1. And then let's see, at negative 1, I'm going to get 1 plus 1, which is 2 here. So we're looking at this segment. Let me shade it in a little bit darker. So what the mean value theorem is saying is that there's some value of x where the average value of the function, so our is a y value on the graph. Sorry, I was getting a little distracted there. So here's my average value, y equals 2. Right? And then we can see visually right about here as a y value on the graph. So here's some x value. And again, we're calling that x equals c in that theorem, the mean value theorem of integrals. So we can see in this particular example, there is one value. Now it looks like from our rough sketch that that value of 1 looks like is where that average is. But if we don't have a very simplistic example like this, right here would be our approach. Right, so we would basically say something like this. We would say there's some value x equals c that equals the average of the entire function. So our average being 1 over b minus a, the integral from a to b of f of x dx. So for this specific example, we would be saying that we're looking for that value x equals c that equals the average of the function. Now again, we already calculated this whole entire average. We found that average to be 2. So we would be saying, well, we're looking for some value, x equals c, that equals the average value of the function on that interval. And our f of x is 1 plus x squared. So f of c is 1 plus c squared. And we would be solving that equation for c. So I would have c squared equals 1. So I'm going to take the 1 and subtract it to the other side. And then I would square root and get plus or minus 1. Now, we were looking at the interval from minus 1 to 2, so technically there's two values of x that satisfy the mean value theorem. And that is at x equals 1 and x equals negative 1. And again, I'm going to scroll back up for a second here for us to see that visualization. Right, and we didn't see it, or I didn't see it right away. Right, I was looking for a number between 1 and 2, but we can see obviously there's a second number here, right, where we would have this rectangle that is like the leveling out of the curve equaling the average value. Alright, so this video is approaching 30 minutes, and you guys know at this point I don't like my videos to get too long. Probably in a classroom environment I'd have my students do a couple more examples and work on them together. So obviously that's really what you should do at this point, right? Go into your textbook or where you're working on homework and practice this. Now, just to mention to you that at this point, right, we're approaching the end of a chapter which focuses on applications of integration. So we're just doing integrals here to calculate an average value. So whenever you're calculating these integrals that we have here, right, integral of f of x dx, think about your techniques of integration, that you're going to be involving there, right? You might be using the power rule like we did with the polynomial 1 plus x squared. You know what I just noticed? I apologize. I had a typo here. It is Monday and my brain's not working. I don't know why I squared that function. This was 1 plus x squared. That's my f of x. So anyway, when you're doing these integrals, think about your techniques of integration. Sometimes you're integrating in e to the x, which is e to the x, or sometimes you're integrating sine of x, right, which is negative cosine of x. Sometimes you're integrating where you need a u substitution. So some of these problems might be a little more intricate in the sense that your technique of integration would vary or change. But overall, the concept is we're finding the average value of a function. Remember, the true beauty of mathematics here is in its application. So we looked at that example where we found the average velocity of a car, traveling car. And usually in a textbook you have some other types of applications, and classic applications usually involve like average velocity or average temperature, right? You might have a function that calculates temperature and you're finding the average temperature. You might have a function that calculates profit or cost in a business situation, and you're finding average profit or average cost. Okay, that's everything I want to discuss in this video. I look forward to seeing you guys in the next video.